Okay, so good morning officially. All right, so we are going to do another quiz on Friday, of course. And uh, I don't know, just kind of, it is just the three of us right now. And I said I would put it out to the class. It's just kind of hard to gauge how people feel about maybe just making the quiz kind of outside of class time, because I am a little bit short on time. But I don't love that idea either. So how about we keep quiz 3 during class time, um, and then we've got the test, our first test next week, right on Thursday before reading break. So um, not Thursday, Friday. Looking at the wrong class. It's easy. All my classes have tests before reading break. But we're on Friday. So it's going to be on kind of as much as we have covered in chapter 2. Might not get through all of chapter 2 because there's a lot of stuff going on here. As a light at the end of the tunnel, once we get into chapter 3, things will kind of calm down and we'll kind of be on the right track. We just need to get through chapter 2, which is limits, and no one likes limits, but we have to do them to build up to chapter 3. So, but once we get into chapters 3 and 4, I think you'll find that everything just kind of smooths out, or hopefully. So part of me just wants to get through chapter 2. It's not that fun, but okay. So we'll have quiz number 3. Again, we'll do it on Friday, and I'll schedule it for 10 to 10:45. Okay, and then we'll start class after that. And then start class after. Okay, just to kind of see where everyone's at. And it'll be 2.1, 2.1, and up to the end of today. Okay, so wherever we get to today, I'm hoping to wrap up 2.3, but we'll see. So we will see. But just kind of to the end of today. So 2.1, we kind of established the idea of a limit, and same thing in 2.2. We're just going to keep working with limits. In 2.1, we just plugged in values, multiple values, many values, as you've probably seen in the assignment, right? You just plug in values into the function and to see how that function behaves around some number. We're going to get a little bit more sophisticated than that, but that's the general idea. Okay, so let's see here. I want to do a review, but I can't really remember what we finished on. So just kind of as a quick review, what we said. We calculated limits at x equals a by finding f of x at values close to x equals a, at values close to x equals a. Right, so if you want to find the limit at x equals 2, for example, you might do values like 1.9, 1.99, 1.999, right? You can get infinitely close. You can chop it up, right? You might grow bored, but you can get really close to 2 without being at 2. And then you could try 2.01, 2.001, 2.0001, right? So you can get really, really close to 2, but not at 2. And so that's one way that you can calculate limits that we'll kind of keep seeing. But it is really tedious, right? So we need some other methods to do that. I'll say that's the end of our review because what we did last day when we plugged in values, it's not really going to come up as much today. So I'll kind of leave it in the dust. But let's talk about one-sided limits. So we're still in section 2.2. And in case we're kind of lost here, 2.2 continued. Yeah. So hopefully you have the 2.2 handout. We're talking about one-sided limits. Okay. So there are limits that do not exist, okay? And then there are limits that maybe only exist from one direction, right? And so we're going to talk about one-sided limits. So you can come in from the left or you can come in from the right to a point. And eventually, spoiler alert, what we'll find is that the overall limit only exists if those two limits are the same, right? So it just kind of, that's where we're headed, but we're going to build up to that. So you can have a left-handed limit, a right-handed limit, but the overall limit only exists if they're the same. So there are limits. There are limits that do not exist, which we typically just write D&E, does not exist. Okay. And some limits only exist on one, oops, I combined that, on one side. On one side, right? Should be a period. So the Heaviside function is kind of our starting point. Okay, so the Heaviside function, I've included the little description because it's kind of fun to read about. It's not important, but the idea is, okay, so at time 0, so this is what it looks like. Not a very fun graph to look at, right? It's 0, 0 for all values of x, or time in this case. So here it's 0, 0, 0, and then at time 0, it switches to 1, right? So it's jumping between 0 and 1. And this is an on-off switch for power, or a light switch maybe, right? And so up until time 0, it's off, and then it switches on, right? But what we can see here is that those limits aren't the same. So the limit from the left exists, right? The limit as we're coming in from the left is 0, right? Y equals 0. And then the limit as we're coming in from the right, right? So imagine you're coming in from the right. Well, the limit from the right is going to be 1, right? So we have these one-sided limits, but ultimately they're not the same. So we don't have an overall limit at t equals 0. Okay, so this is talking about at t equals 0. So it's an on-off switch, and this is kind of our most basic. The limit doesn't exist, but we do have these individual one-sided limits. Okay. So I'll bring in the graph because that's the one I was pointing at the most. The Heaviside function which we denote by capital H of t, is equal to 0 if t is less than 0, and 1 if t is greater than or equal to 0. Okay. So it switches on at time 0. And we see that the limit of h of t from the left is 0, and from the right is 1, right, from the graph. Often it'll be easier if we have the graph to figure out what the limit is, and especially in this case. Okay. So we need some way to denote mathematically that we're coming in from the left or coming in from the right, right? And so we establish some notation to denote one-sided limits. We use the limit as x approaches a in general from, and then we do a little superscript negative. So this is from the left. Right? Or from the negative side of a, right? So you're coming in from the smaller values of a. So remember how we talked about x equals 2. If we want to find the limit at 2, then typically what we do is we we look at calculations for values close to 2 but less than 2, right? So 1.9, 1.99, that would be coming from the left. And then we look at values close to 2 but from the other side, right, coming in from the right, 2.01, 2.001, etc. Okay, so this is what we call a left-handed limit. Oh, I guess I should finish f of x. This is the left-handed limit. Which will abbreviate LHL. What we're going to find is that a lot of the time we're going to have to kind of justify our work and say, since the left-handed limit does not equal the right-handed limit, so then what we'll be able to say is just LHL does not equal RHL. Oops, if I can write that out. Right, so eventually that's kind of where we're headed, right? Then the limit does not exist. Okay, so we're just kind of developing this shorthand to make life easier later on. Okay. Same thing, if we take the limit as x goes to a from the right, denoted by a little superscript positive of f of x, this means from the right, we'll call this the right-handed limit. Right hand or right hand limit? Right-handed, it's this little person. How about we just call it the right hand limit? And I should probably change it. Left-handed limit. Well, it still works, but it doesn't, I don't know, it just doesn't sound right. Either way. So we're going to look at left-handed limits and we're going to look at right-handed limits. What's nice about it is in the past, right, when we've been doing those calculations over and over and over again, we've been looking at both the left and the right-handed limits, but now we're just told which side to look at, right? Ultimately, we'll probably have to look at both anyways, but sometimes we'll just be interested in one side and then we can really focus on that one side. So I wanted to show you another example of a limit that does not exist. So one limit that doesn't exist is if they're not the same from each side. But then another one that I included here is the sine function. Oops. Okay, so what happens when you have sine of anything over x, really, the limit doesn't exist as you get closer to 0, because as x gets closer to 0, then so you're dividing by this really, really small number, and what happens is it just starts oscillating faster and faster and faster and faster. And so that's just one to look out for, is that if you have the sign of something over x, where that over x is inside the sine function, then as x goes to 0, the limit doesn't exist because it can't make up its mind, right? It's going to go closer and closer, and it's going to jump between -1, +1, -1, +1, da, 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 right? And so here, I want to say that the limit as x goes to 0 of the sine of pi over x does not exist. And sometimes, okay, so here's just kind of heads up. Sometimes I'll say equals does not exist. That doesn't really make sense, right? If it's equal to some number, it should exist, right? And so sometimes I'll throw in the equal sign, but I'll try not to, right? And so I encourage you to kind of try not to, but it's not a big deal if you say sine of pi over x equals does not exist. But that's just kind of a thing that I'm keeping in mind for myself. Okay. And here I'll just explain, since the value oscillates faster as x goes to 0. Okay. So that's not something that I expect you to know or anything like that, but now I've told you so.
Question.
So now it's something that we've added. Sorry, say that again, David.
Quick question. Would that have anything to do with the fact that it's close to or like equal to vertical for the graph, so that the slope isn't essentially, or is that?
Oof. Now
No?
you're asking tough questions. So the problem is, because we're essentially dividing by a really small number, right? As x is approaching 0, but
Actually,
I'm not actually sure about the behind the scenes mechanisms. Like, why does it oscillate faster? I know it has to do with dividing by
actually,
a really small number.
Well, as x is approaching 0, it will theoretically reach 0, ergo it results in it being undefined.
Yeah. So the problem is we can't divide by 0, but we can get close. But then the way the sine function works is it's just going to keep like being indecisive close to x equals 0. But
so a short answer, or it's complicated.
Yeah. Will you accept that? Okay. Yeah. I don't know. Can look into it, but I haven't had to, so you don't have to either. All right. But like I said, the sine of something over x as x goes to 0, that's something that we need to kind of remember, that, okay, that's when it starts getting out of control and starts kind of oscillating faster and faster. So that we do need to remember, but other stuff. All right. So those are two ways that a limit might not exist. Okay, so what we said earlier was that if we have some sort of function like this, and maybe I'll just copy all of this in here. Okay, so here, if I've got some function, right, in pink here, then what I have, right, if I'm interested in the limit as x approaches a, then essentially what I'm doing is I'm moving closer and closer to A, and this is the left-handed limit, right? So as x approaches A from the left, right, then f of x is going to go to L, right? So typically when we denote the value of a limit, we'll use a capital L, right, just as a placeholder. And then so same thing if x is approaching A from the right. So here we're kind of approaching A from both the left and the right. And then here's the moneymaker, which I'll put kind of big yellow around. So the limit as x approaches A of f of x is equal to L if and only if the left-handed limit equals L and the right-handed limit equals L, right? So here, the overall limit, so that's what we kind of sneak previewed earlier. So the overall limit as x goes to A only exists if the left-hand limit equals the right-hand limit. Okay. So now we've said it, now we can use it, right? And so let's see here, I've got a little example in there. So we've got a graph, oops. Make sure to include all of it. Uh-oh. All right, do two, making a mess here. Okay. Make this bigger. So if we've got this function, we can call it whatever we want. Let's call it g of x, right? Just to kind of, so we don't get stuck calling it f of x, right? We can call a function whatever we want. We typically call it f of x, but g of x, that's a good choice too. So we've got the graph. And sometimes, I mean, if we have the graph, then finding the limits is really easy, right? So then we can just look at what's the y value at these points. And so the limit as x approaches 2 from the left, right? So here I'm coming in on g of x and I'm approaching x equals 2 from values from the left, right? And so here what I end up at is I end up at 3, right? Y equals 3. And so the limit as x approaches 2 from the left is going to be 3. So here, I'll just kind of jot it down here, equals 3. Okay. You can already see from the graph here that the limit at x equals 2 is not going to exist, right? Because you can already see that those limits aren't going to be the same. But let's do the limit as we come in from the right. So the limit as x goes to 2 from the right of g of x is going to be 1, right? And so we jump down to 1. So then what we said was, okay, well, this limit will only exist if they're the same. And so the limit as x goes to 2 overall of g of x, right? So no left or right notation here. So overall, it doesn't exist because the left-hand limit is not equal to the right-hand limit. Okay. The next part is looking at the limit at 5, right? So the limit as x goes to 5. So here's kind of an interesting situation that we're going to be dealing with more later on. So g of x is defined at 5, right? It's here at, I don't know, a little bit over 1 probably, right? So it doesn't matter what it is, but it is defined at x equals 5. However, as we come in and approach 5, right, our limits seem to be at about 2, right? And so they're approaching the same value. So the limit of g of x at 5 is actually just going to be 2, right? Regardless of it being defined at x equals 5. Okay? And so that's kind of a warning, because I know, and I did it too, right? When I was taking Calc 1, all I wanted to do when I was finding limits was I just wanted to plug in the value and just be done, right? But a lot of the time that's not going to work. And especially if you've got a situation like this, right? So here, the limit as x approaches 5 from the left looks to be about 2. And then same thing from the right, we're coming in on y equals 2. So the overall limit is 2. This is despite g of 5, which is roughly, well, I can say it's not equal to 2. That way I don't need to know what it is roughly. Because it looks like it's a little bit over 1. That doesn't matter, right? All we need to say is that it's not equal to 2. Okay. Good. So that's kind of going to be our go-to. Does the limit exist? Are they equal to each other? Another way that limits might not exist are infinite limits. Okay, so let's see here. Another way a limit does not exist is if we have infinite limits. Okay. So infinite limits are when we have situations like, and because I've got a page break here, I'll just kind of squeeze it in. But if we've got something like this, right? Or maybe even like this. So then here's my axes, right? So here, as x goes to 0 from the left, things are shooting up towards positive infinity and up, up, up. We've seen those asymptotes before, right? Probably in a previous course, right? Where we've got these vertical asymptotes, and same thing as we approach x equals 0 from the right, we're shooting up towards infinity. Remember, infinity is not a number, and so it can't be a limit. But what we do is we, so the limit doesn't exist. That answer is correct, but we get a little bit more specific, because then we say in the sense that it's approaching infinity, right? And so let's see here. Infinite limits. Let's do example 8. So we want to find the limit as x goes to 0 of 1 over x squared. So right away, right, we know we can't divide by 0. So that's trouble, right? So we know that this function doesn't exist, or it's undefined at x equals 0. But what about as x approaches 0? So we want to know, how does it behave from the left and how does it behave from the right? So we know 1 over x squared is undefined at x equals 0, right? Dividing by 0, that's illegal math. Yeah. But we can try values close to 0. Close to x equals 0. Right? Now I've cheated. We've got that table. So now again, we're plugging in values into the function, values close to x equals 0, but not necessarily at x equals 0. So here, they've kind of cut down some of the work here because we've got x squared, right? If I put in a negative into a square, it's going to return the positive, which behaves the same way as the positive value, right? And so it's going to behave the same whether I put in +1 or -1, right? So regardless, 1 over x squared is going to give you 1, right? And so they've done the same thing for values getting closer and closer to 0, but not at 0. And we can also look at the graph, right? We see that things are kind of taking off on either side, going to positive infinity on either side. Okay, so we say that the limit doesn't exist, right? But like I said, we kind of specify how it doesn't exist, right? And so it's technically correct to just say that the limit doesn't exist or does not exist. But in terms of marks, I need to see whether it's an infinite limit or if it's because the limits aren't the same, right? And so technically correct to just say the limit does not exist, but you need to tell me how it doesn't exist. Okay. So we say that the limit as x goes to 0 of 1 over x squared does not exist. Okay. But we write, and I'll underline that, but we write the limit as x goes to 0 of 1 over x squared equals infinity. Okay. And that's to describe the fact that, well, the left-hand limit is going to positive infinity and the right-hand limit is going to positive infinity. So in that sense, the left-hand limit and the right-hand limit are essentially the same, right? So then we can say, okay, well, overall, this thing is going to positive infinity. It's blowing out to positive infinity. So this is to describe the fact that the limit as x goes to 0 from the left of 1 over x squared is equal to positive infinity, and the limit as x goes to 0 from the right of 1 over x squared is also positive infinity. Right, I'll just make a note here. They're the same. Whereas, if you think about just 1 over x instead of 1 over x squared, now you don't have that square, and so the negative values of x are going to behave differently than the positive values of x. And if you kind of remember the graph of 1 over x, right, you've got this kind of situation. And so now they're not going to go towards the same, they're both going to go towards infinity, but one's going to go towards negative infinity, and one's going to go to a positive infinity as x goes to 0. So whereas if we look at the limit as x goes to 0 of 1 over x, right? And if I just kind of draw 1 over x here, I'll use different colors. 1 over x, remember, kind of looks like this. Hey, it looks like it's crossing the y-axis. That's not true. There. Dealing with a page break again. So here, right, as x goes to 0 from the left, right, from the left, all those values are negative, right? So now we're going to blow up, but in the negative direction. Okay. And then here, all our x's are positive, so now we're blowing up in the positive direction. So what we're going to find is that it's going to be really useful to kind of remember, or think of it this way. Think of 1 over a big number, or sorry, a small number. Right. As you're approaching 0, you're dividing by really, really, really small numbers, right? And so that's going to give you a really, really big number, right? So that's going to be kind of good to keep in mind, right? If you're dividing by x, and x is getting really, really small, right, towards 0, depending on if it's positive or negative, right, in this case, then 1 over x, as x goes to 0, is going to give you a really big number. So automatically you're going to have this behavior towards infinity, okay? Whether it be positive or negative. So, right, from earlier, we said that the limit as x goes to 0 from the left of 1 over x is negative infinity, and the limit as x goes to 0 from the right of 1 over x, right now all of your x's are positive. We can write it as equal to infinity, but then therefore the limit overall as x goes to 0 of 1 over x does not exist, because they're not the same, right? We've got these one-sided limits that we can talk about, but they're not heading in the same direction like they were earlier in 1 over x squared. And so we say that overall the limit doesn't exist. It's not behaving the same way. Okay. Let's see, what did I want to do next? Okay, good. So got a couple more definitions, but in general, we've already talked about them, so no biggie. Okay. I'll bring them both in here. So that we can talk about them. So you probably noticed that we're not doing section 2.4. 2.4 goes through and talks about the precise definition of a limit, and it involves epsilons, and it's just kind of like really kind of, you have to trudge through it. We're not doing it, but feel free to have a look in section 2.4. It's kind of interesting, but it's not something that you need to know. So here we're going to talk about the intuitive definition of an infinite limit. And so if we've got a function and it's defined on both sides of a, so remember 1 over x, for example, right? It's not necessarily defined at x equals 0, right? But it's defined everywhere else around x equals 0. It's defined. So then here, if we write the limit as x approaches a of f of x is equal to infinity, what we're saying is that f of x, you can make it as large as you want by moving x, or moving x as close to a as you possibly can, right? So the closer you get to a, thinking back to 1 over x, right, the closer you get to 0, you're dividing by a smaller and smaller and smaller and smaller number. And so the result is getting larger and larger and larger and larger. Right? And so that's just what we mean by infinite limits. So like I said, we've already talked about them, but I threw around the term vertical asymptote, but here it is again. So the vertical line, if you've got this kind of infinite behavior around x equals a, we call that a vertical asymptote if at least one of the directions or both are heading towards one of the infinities, right? Positive or negative. So if at least one of these following statements is true, right? So x is going to a, is going to infinity. What does that mean? We said, okay, if the overall limit as x approaches a is positive infinity, it means that both the left and the right-handed limits are going towards positive infinity. Same thing here. If they're both heading towards negative infinity, then we can say that the overall limit is negative infinity. And then we can talk about the one-handed limits, or the one-sided limits, I guess. One-handed. Right, so we can talk about the one-sided limits, but ultimately, if you have any sort of behavior towards infinity, then you've got a vertical asymptote there. Okay. So let's do an example using this stuff. Sure. I included the graph just so we can kind of look at it, right, if you want to. But I would say, and Desmos has kind of let us down on one of those assignment questions where we weren't able to see, but overall Desmos is still really good. So if you're looking around, x equals 3 for 2x over x minus 3, let's just graph it in Desmos just to see what this thing looks like. Because like I said, it's always going to be easier. If you have the graph, then finding these limits and kind of convincing yourself of these limits is going to be so much easier. So 2x over x minus 3, let's just give that a graph. And, oh, it's a different class. 2x divided by, and I want to make sure that everything is being divided by, it is, x minus 3. So if I zoom out a little bit here, okay, it looks like as I approach 3, right, which makes sense because x minus 3 is in my denominator, I know x equals 3 is not in my domain, right? So I already know, because it's not in the domain, I already know that there's something going on at x equals 3. I don't know exactly what, right? But there's some sort of weird behavior at x equals 3. So if we're looking at the limit from the left, well, then from the left, as we approach 3, we're going down towards negative infinity. And then from the right, we're going up towards positive infinity, right? So let's see here. How do we kind of talk about that mathematically? I'll bring in the graph instead of trying to draw it out. So from the graph, graph. I don't know why I wrote that. From the graph, we see that the limit as x approaches 3 from the, and we're starting with the positive side. It's a little bit hard to, at least when I look at our shared screen here, it's a little bit small, but first from the right and then from the left. So the limit as x approaches 3 from the right of 2x over x minus 3 is going to be positive infinity. Right? And the limit as x approaches 3 from the left of 2x over x minus 3 is negative infinity. Okay. But we need to be able to communicate this mathematically, right? But we also need to be able to communicate this mathematically. Okay. So what we're going to do is we need to think about, okay, so x equals 3, when I put in values close to 3, and I'm going to break it up and talk about from the left and then from the right, or maybe I should do it in the same order here, from the right and then from the left. Doesn't matter, but so kind of, maybe I should put quotes around mathematically. You'll see what I mean in a second here. But if x is close to 3, okay, but larger than 3, so from the right, so if x is close to 3, but larger than 3, okay, so that's as x is approaching 3 from the right, right? Then if we look at this function, and of course we're talking about the same function in either case, right? But if we're looking at values larger than 3, approaching 3 from the right, then 2 times something close to 3 is roughly 6, right? But we need to keep in mind that that's going to be positive, right? And then x minus 3, if it's slightly larger than 3, will also be positive. It's going to be really, really small. So again, we have this a value divided by a really, really small value, right? And so that's why it's blowing up towards positive infinity. Whereas if we're talking about as we approach 3 from the left, now this value is just slightly less than 3, right? So 2 times something slightly less than 3 is still roughly 6, still positive, right? But then if I think about something like 2.9 minus 3, right? 2.9 is close to 3 from the left, but not at 3. I'd want to get closer to 3 than 2.9, but just to get the idea, now I'm dividing a positive number by a negative number, and that negative number is going to get really, really, really small, right? And so that's why it's blowing up towards infinity, but it's going towards negative infinity because of that negative behavior. That was a lot. Let's write that down. So if x is close to 3, but that's what we're writing here, okay? So if x is close to 3, but larger than 3, so if x is approaching 3 from the right, the denominator and remember, it's the numerator over the denominator in a fraction, right? And so I always, well, now I don't because I say it all the time, but when I was first kind of getting into math, I had to think, okay, numero uno, that goes on top, so that's the numerator, and then the other one is the denominator. Right? So whatever you need to do to kind of solidify this terminology, you gotta do it. Numerator, denominator. You need to keep those straight. So the denominator is a small positive number. Okay. And the numerator to x is close to 6, right? Also positive. Mhm. So then the fraction, or the quotient as we can call it, so the quotient (2x over x minus 3) is a large positive number. Is a large positive number. And just thinking about how positives and negatives react. And so therefore we can say that the limit as x goes to 3 from the right of 2x over x minus 3 is positive infinity. Okay. So like I said, I kind of caught myself here. We also need to be able to communicate this mathematically. We're not really doing anything mathematically, but we're justifying it mathematically, right? So we're talking about how does 3 behave, how does x behave close to 3 but not at 3 from the right, right? And so we can do the same thing from the left. So if x is close to 3, but less than 3, then I'll just say x is going to 3 from the left. The denominator, x minus 3, is going to be a really small negative number. The denominator is a small negative number, while 2x is still close to 6. Still close to 6, right? And still positive. So now you've got a positive over a negative, right? Which would give you a negative value overall, right? So therefore, the limit as x approaches 3 from the left of 2x over x minus 3 is going to be negative. Oops, that doesn't look like infinity. Negative infinity. Okay. We see, right, both from the limits and graphically, right? If you have the graph, then you can use the graph, right? But from the limits, especially, we see that we have this vertical asymptote. So we see that the line x equals 3 is a vertical asymptote. Mm-hmm. Okay. So that idea of dividing by a really, really small number is going to make things explode, right? We're going to use that. And especially if you have a fraction, right? As soon as we've got a fraction and it's possible to divide by 0, we need to be kind of weary around that value that's not in the domain. Typically, there is a vertical asymptote there, not necessarily, but typically, right? And so then we need to figure out what the behavior is around that point. Okay. So let's have a little break before we start the next section. I don't know what time is it, 10:56. Not much of a break, but a little break, enough to grab some water. David's back. That's the only way I can tell if we're ready to go. It's all right. So, okay. Let's get into the funner parts of limits. Not necessarily fun, but more fun. Funner. 2.3, we're going to establish some limit laws that we'll be able to use and apply and just kind of make life easier when we're calculating limits, so that we're not just plugging in tons of different values and just kind of guessing what the limit might be. So section 2.3 is called Calculating Limits Using the Limit Laws. There are lots of limit laws, and I've included them all in the handout, right? You'll see the whole first page of the section 2.3 notes, and I'll make a little scribble here, move it to the top. Yeah. The whole first page, it's just a bunch of facts, right? And so we're going to talk about these, right? And then it's not until the next page of our notes that we actually get some examples and just kind of see how all this works, okay? So I've just kind of summarized all our limit laws here. Well, I haven't, I stole them, but they are summarized here. So first thing we need to establish is that, okay, whenever we see a C, it's going to denote a constant, right? And so here in limit law 3, for example, we have the C, and so that's going to be a constant. We're also going to assume that the limit of f of x as x goes to a exists, as well as the limit of g of x as x goes to a exists. So these things exist. They're not blowing up towards infinity or anything like that. So then, just kind of nice and slow here, if I need to find the limit of something that I can break up to be a function plus another function, then what I can do is I can essentially distribute that limit across the addition, right? Same thing with subtraction, no surprise there, right? And so this limit here distributes inside the brackets, if you want to think about it that way, right? And that's how I think about it. I don't know if that's technically correct. It's probably not, but right, in my mind, I say, okay, if I'm adding these functions together, then I can just take the limit of each little chunk, right? And I'm allowed to do that by limit law number 1. Same thing, limit law number 2, it's just subtraction instead of addition, nothing really wild there. 3 says that, okay, if I've got a constant times a function, right? So if you're thinking about 2x squared, for example, 2 times x squared, well, that 2 would be a constant. And so when you kind of when you float this limit inside, you can bump that constant outside. And so that constant is multiplying the limit. Okay. And it's going to feel like a lot when we're just talking about these rules. But once we do some examples, you'll see, oh, okay, I get it, right? Hopefully. But especially in this first box, right? The name of the game is you can float that limit inside onto the individual functions, right? And so if you have 2 functions being multiplied together, then you can distribute that limit across the multiplication, right? You can take the limit of f of x times the limit of g of x, and then just multiply those limits together to find the limit of the 2 functions multiplied together, right? Same thing with division, as long as the limit in the denominator doesn't equal 0, right? So we'll do an example where we go ahead and we use this fact, and then it's not until we get to the end that we're able to confirm that, oh yeah, this limit doesn't equal 0, so we're allowed to do that, right? If it turns out that it equals 0, which it won't, then we need to figure out another way to do it. Or I shouldn't say it won't. It will, but we'll have ways to work around it. You'll see what I mean. So up here, right, laws 1 through 5, essentially you can float that limit inside the brackets and then calculate the limit that way. Okay. Same thing here. If you've got now a little bit different, right? Because here you've got a function to the power of n, so you've got some exponent here. Then you can float that limit inside, but then you're raising the limit to the power of n, right? So you can float that limit inside onto the f of x and then raise it to the power of n, right? So that's a little bit different, but remember c is a constant. So the limit as x approaches a of c, remember, we need an x to take x close to a. If we're just talking about a constant, well, then it's equal to the constant, right? The limit of a constant is just itself, constant. And then if we just have x, right, just a plain old x, the limit as x approaches a is going to be a, right? Which kind of, I'm okay with that. Should be fine. So here, right, so now we can start combining law 6 with law 8, for example, right? So here, if our function is x, then if we have x to the power of n, right, x to the power of n, that's the limit of x to the power of n by law number 6. So then what we can say is that, well, if the limit of x as x approaches a is a, and then I raise it to the power of n, well, then it's just a to the power of n, right? Remembering that roots are just exponents, right? So the nth root is a to the power of 1 over n, or x to the nth root of x is x to the power of 1 over n, right? So just remember, roots are just exponents. Okay. We do have these kind of conditions, right? I can only take the nth root if n is a positive integer, and then we can only take the even root of positive numbers, right? So I can take the odd root of a negative number. So we have these kind of conditions on here, but they're just extensions of things that we already know, right? I can't take the even root of a negative number. And so if n is even, we have to assume that a is larger than 0, right? And then same thing here, right? I can just kind of float the limit inside. So even if it's not the root of x, I can still take the root of some bigger function, f of x. But what I can do is I'm just allowed to float that limit inside, right? And so it's a limit as x approaches a of f of x, which will hopefully just be easier to deal with, and then take the nth root of that limit. Okay. That's a lot of limit laws. In fact, I think there are a few that I think it keeps going, but these are the ones that we're going to use the most, right? So, and if any others come up, then I'll bring them in. But for now, I guess I'll put them in our notes because we talked about them a lot. But they're also in that handout that I gave you. So. Copy that in. Whee. Oops. Copy. I forgot I had done them like that. Okay. That one's large. There. I'm not moving it. It's just catching up. Okay, so talked about all these, right? But in general, these laws, right? These limit laws are, because that's what they are. These, maybe I'll call them limit laws. These limit laws can be summarized. Summarized by saying that the limit can kind of float onto the functions, right? And so at least in my mind, and this is not like it's not technical in any way, but for me to remember these limit laws, I just think of it, okay, well, it looks like I'm allowed to float this limit onto whatever function I need it to be on, right? So even if you've got some function inside the root here, I'm allowed to float that limit inside because there's a law that says I can, right? And so if you're about to kind of distribute a limit, maybe check the laws that we have here first, right? Make sure that it follows one of these laws, but ultimately it will, right? We'll be able to distribute, can be summarized as we can distribute a limit onto functions I'll say as needed. Not sure that makes sense. It makes sense in my head, and that's how I think about it. And so that's why I want to give it to you guys, but there's probably a better way I could write that. But hopefully I've kind of communicated. Maybe you can rewrite it a little bit better, but you can kind of distribute the limit laws. So let's do an example so we can see what's actually going on here. How does this work? How am I supposed to use this? Copy. So now, right, before, if I gave you a limit like this, what would you do? You would probably take values of x close to 5, but not at 5 to see, maybe coming in from the left, coming in from the right, and evaluate this thing to see what it approaches, and then we can ultimately find the limit, right, or guess the limit. Same thing here, right, as x is approaching -2, we can plug in values close to 2 or -2, but not at -2, and see what this thing behaves like. But now we have the limit laws, so we can just use the limit laws, right? So here I see a function 2x squared minus another function 3x plus a constant, right? So what I can do is I can distribute this limit inside and just look at the individual limits of these things and then subtract or add as necessary. So for A, right, we've got the limit as x approaches 5 of 2x squared minus 3x plus 4. Distributing that limit as x approaches 5 onto each of these terms, I have the limit as x approaches 5 of 2x squared minus the limit as x approaches 5 of 3x plus the limit as x approaches 5 of 4. Tedious to write, right? Writing that limit every time, right? But that's what's going on. Okay, so here, this is, I've just applied laws 1 and 2. Okay. If I think about this as f of x, g of x, and maybe a constant c, right? Or h of x if there was an x involved. So now, to simplify these first terms a little bit more, right? Remember, if we have c times f of x, then we can float that constant outside and just take the limit of x squared, right? And so I can't remember what law, probably 3. Yeah. So by limit law number 3 here, I can float that constant outside. Okay. So I'm going to move this over because I'm going to need a little bit more room here, but the limit as x, oops, 2 goes outside. 2 is a constant. 2 times the limit of as x approaches 5 of x squared minus, again, 3 is a constant, times the limit as x approaches 5 of x plus, and then the limit of 4 as x approaches 5. Well, 4 doesn't care what x is doing, so that's just going to be 4. Okay. So for these first 2 terms, I used law number 3. And for the constant, I used law number 7. Okay. Now, so here we had to evaluate the following limits and justify each step. So it's only when you have to justify each step that you have to tell me which law you're using, right? And really that's just meant to kind of keep you on your toes and make sure that what you're doing follows some law, right? Eventually we're not going to talk about which law we used. We're just going to have them on hand and we're just going to use them. But for now, we need to kind of justify why we're doing what we're doing. So, okay, then I've got, okay, so x squared is the same as x, so f of x equals x, and then that to the power of 2, right? And so, but then we kind of extended that to another law, so x squared, we said that the limit of x to the power of n, where n is a positive integer, in this case it's 2, so that's fine. As x approaches a, we can rewrite as a to the power of n, right? So this is law number 9 that we're going to use. And I think we've got the limit, yeah, the limit of x. Oh, it's a little laggy now. The limit of x as x approaches 5, there we're going to use law, catch up, law number 8, right? So law number 8 and law number 9, we can kind of use pretty easily. Oops. So this is going to be 2 times 5 squared minus 3 times 5 plus 4. So this here is law 9, and this is from law 8. But if you just think about Law 8 could be incorporated into law 9 if you just let n be 1, right? X to the power of 1, but it doesn't matter. Now, I don't have any more limits, right, to calculate. I've already found these limits. And so now I'm able to just calculate this thing. So 2 times 5 squared puts me at 5 squared is 25 times 2 is 50. I'm terrible at plain old math, but that's okay. 50 minus 15 plus 4 puts me at 39. So now I have the limit of this thing is 39. So we've calculated the limit using the limit laws. And you could have gotten here by, substituting in values close to 5. What we're going to build towards is, well, I could have just plugged in x equals 5 here, right? And the reason for that is because this is a polynomial. So we'll establish that and then we'll be able to use that. But for now, right, we can work through it with the limit laws. But ultimately, if you have a polynomial like this, right, good to be able to recognize polynomials. If it's just a string of things, then it's a polynomial like this, then you'll just be able to plug in whatever is at the limit. So those will be the easiest limits to find because then you can just plug in the value and move on with your life. All right. Here, right, we want to find the limit as x approaches -2 of this fraction. And so what I can do first thing is I can distribute this limit into the numerator and the denominator by that quotient law, law number 5. Oops. Come on. Law number 5. And remember we said assuming that the limit of the denominator is not equal to 0. So what we're going to do is we're going to go ahead and use this property, and then at the end we'll just make sure we're not dividing by 0. If we are dividing by 0, I mean that would put a stop to things anyways, so you'll see. So B, we want to find the limit as x approaches -2 of x to the power of 3 plus 2x squared minus 1 over 5 minus 3x. And I'm going to move this kind of closer to the limit because I need lots of room here on the right-hand side. So by law number 5, I'm able to distribute the limit onto both the numerator and the denominator. So let's go ahead and do that. I have the limit as x goes to -2 of x to the 3 plus 2x squared minus 1 divided by the limit as x goes to -2 of 5 minus 3x. And I'll just make a note here that I did that by law 11 to 5. I don't know why I said 11. Doesn't even come up here. All right. So okay, now looking at these limits individually, I'm back to essentially the same situation that I had earlier, right? Where I'm able to distribute this limit, kind of bump out the constants, and I can do that in the same step. So now I can rewrite this as, and I'm going to make a note before we continue here, right? This is assuming assuming the limit as x goes to -2 of 5 minus 3x does not equal 0. Right? Which we'll check later, but that is one of the assumptions that we're heading into this with. So now if I distribute this limit in the numerator and then in the denominator, I get the limit as x goes to -2 of x to the 3 plus 2 times the limit as x goes to -2 of x squared minus, I'm just going to go straight to 1. I'm not going to write the limit of 1 as x goes to -2. I'm just going to go straight to 1. So here's what happened. Here, this is law number 1. Here I used law number 1 and 3. Now I don't expect you to remember the law numbers, but I've kind of got them ready to go in my mind. So shifting that constant outside, I think was law number 3. And because scrolling is proving to be quite a pain here, this is law number 2, and the constant, the limit of the constant was 7. Trying to avoid scrolling. There. It's so laggy. Oh, over the denominator. So again, here. Over the limit as x goes to -2 of 5, which is just 5. So I'm going to bump this over here. 5 minus 3 times the limit as x goes to -2 of x. Cheating a bit. This is law number 7. And this is law number 2 and 3. Okay. So now we have those laws, those handy laws where if I just have x to the power of something, then I'm allowed to just plug in the limit that I'm interested in, right? And I think that was law number 8 and 9. So this becomes -2 to the power of 3 plus 2 times -2 squared minus 1 divided by 5 minus 3 times -2. Number 9. Using that same law for all of these. I think it's number 9. Okay. And now that I don't have any limits here anymore, right? I've been able to get rid of the limits by substituting in the -2 here. So now I can calculate this, right? I get -2 to the power of 3 is -8, plus 8 minus 1 is -1. Womp womp. And then 5 plus 6 is 11. So -1 over 11 is my limit. Nice. So here, right, 5 plus 6 that does not equal 0 that's a good thing, right? That's one of the things that we were going to check. And like I said, if you had gotten here and you had 0 in the denominator, you should have kind of a mental stopper and say, oh, well, I can't divide by 0, so I need to try something else, right? And so that would be the time to kind of, oh, okay, well, that didn't work. What else can I do? Okay. So what I want to do is I want to give you some tricks to have up your sleeve for when things don't work, right? So for when you're going to end up dividing by 0. And most of the time, that's what's going to happen. You know, I'm going to give you a function that you can't just plug in a value and find what it is. Usually I'll give you, you know, 1 that'll be easy to find, like the 2 that we just did. But usually you'll need to kind of manipulate the function a little bit in order to be able to evaluate the limit. But before we do that, let's establish, so what we said before, right, is that if we have a polynomial or a rational function, right, a rational function is a polynomial over a polynomial, okay, and A is in the domain, that's going to be the important part. Then what you can do is the limit as x approaches a of f of x is just the function at a. Okay, so that's going to be really kind of handy, is to be able to recognize a polynomial or a rational function. And as long as and a is in the domain, right? So as long as a is in the domain, so I'm allowed to put a in, then for a polynomial or a rational function, I'm allowed to just plug in the value of a and evaluate the function. Okay. Let's do an example here where it doesn't work right away, right? So here, this as a note is a polynomial over a polynomial. Right? X squared minus 1 is a polynomial, x minus 1 is a polynomial, which a polynomial over a polynomial is a rational function. That's what it's called. So it does fit into this category, right? But the problem is that a has to be in the domain. And so as x approaches 1 is not in the domain, right? And so here I'll do it in red. Notice x equals 1 is not in the domain. So you can try, right, as soon as you see a rational function like this, you can try, okay, I'm just going to plug in 1 squared minus 1, okay, fine, it's 0. And then 1 minus 1, that's also 0, right? I can't have 0 in the denominator. So then your next thought is going to be, okay, well, what if I try to factor this thing, x squared minus 1, and I try to manipulate this function so that I can plug in x equals 1, right? I can manipulate this function without changing the function to evaluate the limit. And so that's one of the tricks that we're gonna use. So we can try to manipulate the function, right, without changing it. To find the limit. Okay, so one of the options, and probably it'll be your go-to option if if you come across this situation where if you just plug it in, it's not going to work, is to factor and cancel. Okay, so try factoring and canceling. So you can manipulate it a little bit without changing it, and then try to find the limit. Okay. So if we think about the limit as x approaches 1 of x squared minus 1 over x minus 1, looking at this thing, right, x minus 1, I have a vague memory of x squared minus 1. I can factor, right? It's one of those special factors, but even if you don't recognize that, x squared minus 1, you can write as x squared minus 1 squared, right? And so, but just try pulling out a factor of x minus 1, right? Because that's ultimately what you want to get rid of. That's the one making trouble. And so if you can pull out x minus 1 from here, then you're kind of off to the races, right? And so this you can rewrite as the limit as x goes to 1 of x minus 1 times x plus 1 over x minus 1. And I'll put it in brackets just to emphasize that they're the same, right? X minus 1 over x minus 1. So I don't want you to be kind of disheartened by, okay, because I remember feeling, oh, I didn't see that I could factor this immediately, right? And I don't have those factors, those special factoring formulas memorized yet, right? But what I want you to see is, okay, x minus 1, yeah, I think I can factor that out from x squared minus 1, which you can rewrite as x squared minus 1 squared, right? And so just kind of approach it that way and see if you're able to cancel this troublemaker out, right? And so here, just to show that I'm canceling in a different color here. So now what I'm left with is I want to take the limit as x approaches 1 of x plus 1. Well, that's fine. Technically, I can distribute the limit, but because this is a polynomial, right, x plus 1, then I've got that property that says, well, it's a polynomial, so I can just plug in x equals 1. So this is 1 plus 1. And I'll just make a note here that this is a polynomial, right? And so I've got that property that says, okay, I can just plug in the values. I think it's called the direct substitution property. So the limit then is 2. Okay, good. Let's bring in this last, well, maybe second to last fact. Copy. So that's one of the tools that I need you to have up your sleeve, is kind of canceling whatever is giving you grief, right? Or try to, so manipulating it without changing anything. So another kind of thing we can use is if we have a function f of x that's equal to g of x, so another function, when x is not equal to a, then the limit as x approaches a, right, of f of x is equal to the limit of g of x as x approaches a, assuming that both of the limits exist. So essentially what it's saying is that, and this is kind of what we used already, is that if I can rewrite a function into another function, right? So they're the same when x is not equal to a, right? Then the limits of these two things are going to be the same, right? So this is the property, and I guess I should have put this property above, but this is the property we used above, right? So we said if we let f of x in kind of this case here, f of x was the original function, x squared is equal to x squared minus 1 over x minus 1. F of x is the original function, and then we manipulated it to be g of x, which is just x plus 1, okay? That's only true when x is not equal to 1, right? As x approaches 1. When x is not equal to 1, right? So here, right, we said, well, if I'm taking the limit of this thing and I've changed f of x, right, to be g of x as long as x is not equal to 1, right? Because then it's not in the domain, right? And that was the problem, right? So it's kind of a catch-22 here. Then by this property, right, I can say that the limits are going to be the same. So let's do another example. And so with these examples, I've got quite a few examples here. I just want to give you a couple of tools that you can try, because like I said, most of the time, trying to plug in the value into the limit, it's not going to work, right? You're going to end up dividing by 0 or potentially taking the square root of a negative number or both, right? And so we need ways around that, right? Did I copy this already? Who knows? So here, in example 5, if we have to evaluate the limit as h goes to 0 of 3 plus h squared minus 9 over h, well here, right, I can expand this out and it would be a rational function, right? Because I'd have a polynomial over a polynomial. The hard part is that h is going to 0, which is not good. H equals 0 is not in the domain, right? And so here, h equals 0 is not in the domain. All right, so we need some way around that. What we can do, and this is just going to be a matter of, you know, practicing enough of these problems to kind of recognize, oh, last time I had one of these, I tried this and it worked. So and I know that's annoying, especially when you're beginning, but in this case, right, when I'm scanning this problem, I see, okay, well, I can expand 3 plus h times 3 plus h, and I would end up with a 9, which would subtract this 9. And so maybe that will help me cancel this h. So again, just like we did before, I'm trying to eliminate the problem child here, right? H in the denominator. So I'm trying to kind of morph this from a function that doesn't work to one where I can just plug in h equals 0 and find out the limit. Okay, so we can try, right? Try to eliminate, oh, office hours later, okay. the h in the denominator by maybe expanding and canceling. All right, so there's no set rules for these things, but ultimately you're trying to get rid of that h in the denominator, whatever way you kind of see. Okay, so what we can say is that the limit as h goes to 0 of 3 plus h squared minus 9 over h, that's going to be the same thing as the limit as h goes to 0. Now, you might be tempted to not write the limit every time, but to be technically correct, you have to write that limit every time. And I know it's annoying, and I know it's always there and whatever, but you need to show it. Okay, so of 3 plus h times 3 plus h minus 9 over h. Right. So far, I haven't changed the overall function, right? But I will once I expand this thing and cancel those 9s. So I have the limit as h goes to 0 of 3 times 3 is 9, plus 3h plus 3h, so plus 6h plus h squared, then minus 9 over h. So what I have, I can cancel those 9s. And just to emphasize, I'm going to pull out a common h, a common factor of h from both of these terms in my next step. So I have the limit as h goes to 0 of h times 6 plus h over h. That h over h is going to go to 1. Now I can find the limit of 6 plus h as h goes to 0 is just 6 plus 0, which puts me at 6. The limit as h goes to 0 of 6 plus h, 6 plus 0 is 6. All right. So I'll keep showing you a couple of massaging tricks that you can use, but like I said, it's all going to be kind of practice and seeing enough of these to kind of be like, oh, okay, I can try this. Maybe it'll work, maybe it won't. Right? All right. We'll end it there. So our quiz on Friday will cover up to here. Right, so limit laws. There's a little bit more in section 2.3 that we haven't covered, but I'll leave that for the test, I guess.
In that case, I've got a question for the
Sure.
Webassign Assignments.
Mm-hmm.
The due date on the 2.5 one is also on Friday.
I'll bump that. Yeah. It was wishful thinking.
We're doing our best here.
Yeah.
In that case, I shall see you Friday.
Awesome. See you Friday.